Today's topic is refraction. And refraction is, again, something that in everyday life we do actually have a lot of experience with. If you have a glass and you have a straw stuck down in your glass, and you can see that that straw, even though it was straight when you put it in the glass, it appears that that straw bends once it's down in your, especially if you've got a clear liquid in there, and it looks like that straw is bent. Another place where you might have noticed this, at least we did this when I was a little bitty gal and I was taking swimming lessons when I was real little. Our teacher would always throw quarters into the water, and her goal in doing that was because she wanted us to go under the water and have our eyes open so that we could see where the quarter was and pick it up. Well, I have to admit, I always cheated because I hated opening my eyes under the water. So I'd always find the quarter with my toes and then I'd go down and get it. You weren't supposed to do it that way. But at any rate, the reason that you can't just look at it and go down is because the light rays refract when they go from the air down into the water. And so you can't just look at it and assume that you've got it in the right place. Because it's the light rays bend, and that quarter is not where it appears to your eyes to be. Here's another way to think about it. Let's say that here's your boundary between the air and water. And so you have a light ray that comes in at this angle. And just like we talked about before, if I have a perpendicular constructed at that point of entry, part of that light ray is going to reflect back off. And so here's your angle of incidence, here's your angle of reflection, and these two angles are going to be equal to each other, just like they always are, just like the law of reflection states. Angle of incidence is going to equal the angle of reflection. But when the light ray goes down into the water, and we know part of it has to go into the water because we can see underneath the water if there's not too much junk in the water, what happens to that light ray then? Well, there's a couple of different analogies I can give you to explain why this happens the way that it does. The light ray is actually going to bend. If you have ever seen a marching band, let's pretend that we have a nice straight line in a marching band, and they're marching this direction across the football field. Okay, so they're going this direction, and the same direction as the incident light ray is in our example. Except in place of air and water, what I have here is I've got grass and I have mud. And so this nice straight marching band line, this end of it, if they're going like this end is going to encounter the mud first. Now, this marching band is exceedingly well trained, and so every time they take a step, they are supposed to make sure that their foot hits the ground at the exact same time that everybody else's foot in the marching band hits the ground, and they always all take the same length of step. Well, when this end gets down here and they hit this really, really sticky mud puddle, they're having trouble getting their feet out of the mud so that they can take their next step. And so they are delayed in getting their foot out. So in order to get their foot back down at the same time that everybody else does, they don't have time to move their leg forward as far. And so what happens is that this end of the line is going to actually keep moving faster than this end is going to be able to go. So this end comes down here, this end has to slow down, this end is moving faster so that this line is going to swing around this direction because this end's getting its feet stuck until everybody gets in the mud, and then they're going to be able to straighten back out into their nice straight line again. Here's another way to think about it. If maybe this example is a little bit out of reach for your brain, try it this way. Let's say that I have a vehicle. Maybe I've got a relatively large truck, and he comes along this way, and he hits either mud or he hits water. And so when he gets down here, his front if he's going this direction, it would be his front right tire. His front right tire is going to hit first. Well, it gets into either the water or the mud and it can't roll and it starts spinning. And so if it's not making any forward motion, what happens is that this vehicle then starts to fishtail and it kind of goes this direction, okay? Because this end's stuck and the rest of it keeps going like this. So what that means is that this light ray, by analogy, is going to, in place of going, this is where it would have gone if it went straight through, but instead it's going to bend and it's going to go through down here instead. So it's going to bend towards this perpendicular line away from the path that it would normally have gone. So this is the angle of refraction. And so if you go from a substance that is less dense into a substance that is more dense, then you're going to have a light ray that's going to be refracted towards that perpendicular. Okay, now there has been, as I'm sure you're not surprised, a mathematical law that explains all of this. It's called Snell's Law, and that law says that N1 times the sine of theta 1 equals N2 times the sine of theta 2. Well, theta 1 is the angle of incidence, and theta 2 is the angle of refraction. And so if I take the sines of those, they're going to be equal to each other based on what this n is. Well, what is this n? This n is called the index of refraction. And it's going to vary depending on each particular substance. N is actually the ratio of the speed of light in air to the speed of light in the substance. And so your index of refraction, if it's in air, then obviously these two numbers are going to be the same, and the index of refraction of air is going to be 1. In any other substance, light is going to travel more slowly because it is that substance is going to be more dense than air, and so therefore n is going to be greater than 1 for any other substance. So here, the index of refraction is going to be equal to 1, and in water, the index of refraction is going to be greater than 1. So if you have a substance going from a smaller index of refraction to a greater index of refraction, this line is going to bend towards the perpendicular, just like we've already talked about here. Now, you can have light rays that are going to go the opposite direction. They could be, you could have a spotlight under the water, and you could shine it up through the water so that it goes out into the air. Well, if that's true, then it's going to be bending the other way. So if the light originated down here, a straight line would have it coming up more through this general area here, but when it comes through and it gets into a less dense medium, it's going to bend away from that perpendicular. Okay, so you're going to need to be able to keep straight in your mind which way these refracted beams are going to bend. Are they going to bend towards the perpendicular, or are they going to bend away from the perpendicular? And one of the interactives that I have assigned for you to work within the next day or two is going to help you practice that very concept. Let's work example 12.4 just to make sure that you are able to work an example with Snell's Law. Now, you're not only going to need this equation in working your problems, but you're going to need this equation also. So you want to make sure that as you're preparing your index card for this particular module, that you have both of these on your index card. Example 12.4 says a light beam shines on a pane of glass with n equal to 1.5. If the angle of incidence is 34.5 degrees, what is the angle of refraction? So in the diagram there that you can see that the light ray is going from air into glass. So when I do that, since the light ray originates in air, n sub 1 is the index of refraction of air, which is 1.00. And then it says the incident angle is, I believe it was 34.5 degrees. So 34.5 degrees goes here. And then that's going to be n sub 2, which is the index of refraction of the glass, which they told us was 1.5. Right there. And then they wanted to know what the angle of refraction is. And so that's going to be sine of theta 2, which is what I'm actually trying to figure out. So when I solve for this, you're going to take 1 times 34.5, hit the sine button, divided by 1.5, and then you'll have to take the inverse sine, and you guys should have plenty of practice doing this from when we did all this, all of the trigonometric ratio stuff in the first several modules this year, so that shouldn't be a problem for you. So you should have an angle of refraction equal to 22 degrees. You'll notice that I can only have 2 significant figures because although this has 3 and this has 3, the index of refraction of glass that I was given only has 2, so my final answer is only going to have 2 significant figures. Okay, so you're going to get some practice doing some of these problems, some problems calculating the velocity of light in different media, and then also, again, make sure you go through those interactives so that you can practice saying, okay, is this going to bend towards or is it going to bend away from the perpendicular?